look at the, how many Stokes engine or something like that. Whatever it is, let's just look at the engine alone for a car. So just one factor we are considering, which is going to decide the price of the car. So you have a X variable and you have a Y variable, and then the bias variable, which we call it as the Y intercept, that is beta naught. So beta 1 X1 plus beta naught is equal to Y. So that's how we find the simplest regression model. Now in case we want to have more parameters, how do we estimate that? And another aspect is how do we actually interpret the beta naught and beta 1 values that we have. So if you look at beta naught and beta 1 values for one sample data, they've got something like this. The beta 1 value is 156.9 and beta naught value is minus 6870.1. This into the engine size variable actually determines the price of the car. So if statistically, actually you can look at more parameters. Beta naught and beta 1, through machine learning, by reducing the error, residual error, it was found out. So the orientation of the line, the regression line, is now decided like this. But what was the residual error that you have? Where did you stop to decide on the values of these two parameters? And then, statistically, you can also look at what is the p value, what is the t value. You put a t distribution, or you can find out these kind of values statistically. You must have learned about this in foundations of data science, right? Did you learn about p value in foundation of data science? Or did you have foundation of data science course?
Yes, ma'am, we have.
Okay. So did you learn about p values?
We have that as an elective this semester.
This semester. Okay. Okay. So statistically, the data that we have, why I'm telling this is, by looking at this, actually we have considered so many data points. Let's say, for example, 100 samples, 100 data points. From all of them only, we have come to a conclusion that this is the line, regression line, that approximates the trend in that data. So all those samples, the entire column for every variable for X as well as Y, we will be able to get, you can actually take it as a random variable, because as you add more samples, it should be in this category. It should be in the similar category. Similar samples we should be having. So assuming that we will have only similar samples, you can fit a normal distribution or a Gaussian distribution or some kind of probability distribution function across the sample. Because for x1, you will have so many values. For y, you will have so many values. Taking y as a random variable, x as a random variable. Now x is an independent variable, but y is a dependent variable. It is dependent on x. Y is equal to some function of x. So y is dependent on x, it is a dependent variable, and it is the response variable, predictor variable is x. So this is what we learned earlier. So statistically also you can analyze what is the range of the sample values for x, what is the range of sample values for y, what can be the future values of y, and what can be the future values of x. Not just future values, what can be the other values of x and other values of y. That is possible if you treat them as random variables and use a probability distribution to fit a probability distribution over the available values. You have a column of x, you have a column of y. Across those values, if you put a probability distribution. So once you have a probability distribution, all statistical things are possible. The standard deviation, the mean, the second standard deviation, the variance, normal, the parameters of the probability distribution itself, and then the p value, t statistic values. So many things are possible. And finally, the standard error with the current beta naught and beta 1 value. So all these kind of statistical analysis is possible. Now, if you want to look at more values, so let us just look at this example where you have a full-fledged data set. What is the make of the car? What is the fuel type? Number of doors? What about the wheels? Engine size, horsepower, the RPM, peak RPM, and city MPG, mileage per kilometer. What is the mileage that you get? And what is the price? So this is actually in dollars. So it's fine. Now you have so many parameters that is going to determine the price of the vehicle. So you simply consider price of the vehicle as Y and the rest of them as X1, X2, X3, X4, X5, X6, X7, X8. Can you have Y1 and Y2 for this particular data set? Is it possible to choose Y1 and Y2 here? A value which is dependent on the remaining variables. Which variable is dependent on the rest of the variables? Price is one such variable. Can you pick out any other variable which is dependent on the rest of the variables?
Ma'am, peak RPM can be dependent on horsepower, ma'am.
Peak RPM can be dependent on horsepower, but only horsepower, not the others.
Other
Can peak
factors too.
Engine size also,
RPM?
ma'am.
Eh?
Engine size also, ma'am.
Engine size. Will it depend on the mileage also? Peak RPM?
No, ma'am.
Okay. What about the driving wheels? Forward, rear, rear, front and rear. Number of doors, fuel type. Fuel type also will be, influenced by peak RPM. Okay, so can you identify what are the other factors that can be dependent? Peak RPM is dependent on only engine size and horsepower, not the others? Or can you tell a variable which is just like the price of the variable? Can you tell me any other variable that will be dependent on the rest of the variables?
Excuse me, ma'am.
Yes?
I feel a city mileage will be dependent on everything except for the number of doors.
Okay. Yes. Definitely the mileage would be dependent on horsepower, engine size, the driving wheels, type of the fuel, of course, and peak RPM. Okay, good. Can you think of any new variable which is not there in this list? In this list, but that will be dependent on the rest of the variables here. No idea?
Ma'am, you can consider torque also as a variable which is not included in this.
Torque?
Yes, ma'am.
Okay.
Tank capacity, ma'am.
Tank capacity, yes.
For the range.
But you know, that will be in the list of X's. I'm asking you, can you add one
Top
in the
speed,
list
ma'am.
of Y?
Top speed.
What is that?
Top speed, ma'am. Top speed. Or speed
Top.
from like 0 to 7 seconds or something like.
Okay. What is the maximum speed possible? Okay.
And this
Ma'am,
will be
And
related to max
service
horsepower and
charges.
hmm?
Ma'am, service charges can depend on the engine size, horsepower, mileage.
Right. Service charges.
Ma'am, you can also predict what kind of usage that particular vehicle will be used for, depending on these variables. For example, if you look at
like
When you say usage, what exactly do you mean?
like let's say if you take really high power vehicles like Alfa Romeo, and it has like two doors, so you can make out that it's a sports car. So these are like track cars or maybe race cars. Whereas if you have more if you take cars with higher mileages, maybe they're more city friendly and more commuting vehicles like that.
Okay. The utility of the cars, but you know, the list of cars shown here is very costly ones, right? It's not very popular among the major chunk of the population because of the cost, especially because of the cost, correct?
Yes, ma'am. But if you have other cars also, like if you have a bigger list with other cars, I think you can include that.
Yes, yes, we can definitely include that. You can predict the usage of the car depending on all of these types. Okay, that's an additional information. This is from the customer perspective. Okay.
Ma'am, annual, quarterly, monthly sales, something like that.
Exactly. That's what I was trying to give a clue. Sales, you know, depending on all of this, only the sales. From a customer perspective, this information, you know, cost of the car is enough. But from the seller perspective, from the businessman perspective, or the marketing agent perspective, the marketing division perspective, the sales for this car will definitely depend on all of this type, plus including the price. The price of the car, the remaining items, you know, that is going to decide on the sales of the car. So that way, actually, you can have many parameters, and whose perspective you're looking at, what you're looking at. Depending on that only, you will decide what variables you're going to use. For example, you know, if you want to know the mileage of this cars, you know, you want to answer questions on the mileage of the cars. Maybe the number of doors might be irrelevant. So you can ignore that X variable completely for your problem. Given a data set, you have the freedom to decide on which variable to use, which variables to use, and which ones not to use, depending on what question you want to answer, depending on what you would like to know from the derive from the data set. Okay, so the length and width of the car, the height of the car, you know, you can also the ground clearance. The ground clearance of the car is also important to understand, you know, some of the roads, in which roads it can go. Off-road vehicles are, you know, usually SUV vehicles, off-road vehicles are meant for certain purposes. Some of them, you know, sedan vehicles where the ground clearance is lesser, you know, the usage of such cars, that will actually also decide on the sales, right, for a particular area. Across the country, it is different for a particular area, region wise, if you want to analyze. And the cost wise also, cost, everything is going to matter when you look at it region wise. The terrain, what is the kind of terrain in that particular region, that can actually decide. So if you look at this way, you have the price, engine size, horsepower, peak RPM, length, width, and height of the vehicle, all of them put together. Beta naught, beta 1, 2, 3, 4, 5, 6. You call this as the model, estimating the parameters. So these are the parameters of the model, and you have to estimate it. And that estimation is done using your machine learning from the given samples. So if these are the estimated values, then you have this kind of multiple variables. I mean, just when you say multiple variables, it is all excess, more excess you have. And you go beyond, so you can actually say y1, y2 also, if you include, then it becomes a multivariate. So multiple variables, whenever you consider, you can interchangeably call it as multivariate linear regression for both x and y. So for price estimation, now you have beta naught plus beta 1 into x1 plus beta 2 into x2 plus beta 3 into x3. So likewise it goes on. So once you have this estimate, your model is ready. You cannot visualize this model. The reason is it's beyond 3 dimensions. Every variable here will follow an axis. So you have 7 axes here, 0 to 6, 7 axes. So 7-dimensional space we are looking at for such a data set. Is that clear? So now we have to look at applications. Which is what we need to see, just a list of applications where we can apply regression analysis. So I will ask you some questions given a data set, and you have to tell me whether a regression model will be suitable for this problem. So let me show this data set. Look at the data points. Age of the people, 20 customers are there, and what is their purchase capability, or what kind of purchase attitude, or quantity they have purchased and things like that. Just look at a supermarket. Look at a supermarket. So you want to distinguish between different types of customers. This is the problem. Given a supermarket, there are so many customers coming in and going. You want to categorize the different customers. All the data, all that you have is this particular data set, where the age of the customers is versus what they have purchased. So you get data points something like this. Will linear regression be able to help you in any way answering any question in this data set? You want to categorize the customers because you want to predict future customers. Any new customers, you want to put them in the same category. You want to see if they belong to the same category, things like that. Will linear regression be able to capture the trend in the customer data? If you have to use linear regression, where will the line be? Can you tell me that first? So the input variable is in the x-axis, which is the x. Output variable is y. So y is the purchased items, and x is number of purchased items, let's say, or the price of the purchase, value of the purchased items, whatever. That is your output variable y. Input variable x is age. And of course, you will have a bias variable, which is your beta naught. So what will be the best fit for the line using linear regression? How will it be? Can you tell me?
0.5, ma'am.
Will it be something like this? Like this? Or will it be something, the first point to the top row to the first point in the last row? How will it capture the trend?
Ma'am, I don't think so it can, because it's more of a classification problem.
So you will have a line something like this. If you try to fit a linear regression line, this is how you will get, which means literally only 2 points are falling in the line and the rest of the points are away from the line with a different trend. Actually speaking, one group of points has got a different trend, another group of points has a different trend. Actually, linear regression is not suitable for this problem. We call this type of problem where you need to categorize the data points into multiple group of data points, subgroups of data points. You call that as a classification problem. It is no longer a regression problem. So for a classification problem, linear regression is not suitable. You are trying to put them all into one group. Actually, there are multiple groups. In that sense, you cannot capture the trend for all of them. That is not possible. But what you could do is, for two different groups, you can have a separate. For each group, you can have a separate linear regression line. So ideally speaking, if you have two groups here, two regression lines if you put, you will have a perfect regression line with zero error almost for each subgroup. That is possible. So linear regression is not suitable for this kind of problems where you want to classify the data points. Classification is a different task. Linear regression is a different task. Is that understood? But
Yes,
you
ma'am.
can, yes. Now you can use regression and then slightly modify the model in such a way that you can have a classification. You can do classification. Such a model is called as a logistic regression model. By logistic regression model, you will create a function that is a line or a curve, whatever it is, that actually goes through both of them, most of the points in both the groups, and then if you give a cutoff in the green line here, you can say that these two point groups have been separated. You are able to separate them. You are able to categorize them. You are able to split them into two groups. So something called logistic regression is a model that is helpful to fit, if you fit the model like this, it is helpful in classification. So when you say linear regression, it is not possible to capture, cannot be used for classification problems. Logistic regression can be used for classification problems. So we will, as we go down, we will look at what is logistic regression. So let me give you another example. Now you have to tell me whether linear regression will be suitable or not. I'm only taking very special examples. So this is something called as time series data. Okay. Now looking at time series data, you can see here number of visitors per month as well as the temperature over a time series means, this data 2014 first month, 2014 seventh month, 2015 first month. So monthly data has been marked as data points. So let us look at a Yellowstone Park, right? So it's a park. How many people visited the park in 2014 January, July 2014, January 2015, July 2015, January 2016 and July 2016? How many people visited and what is the temperature during that time? What is the season during that time? This you call it as a time series graph. Now this one, can you use regression for modeling the trend in the data?
Ma'am, I think we can use nonlinear regression to capture the trend.
Yes, linear regression is not a good option. You can't have a straight line because that's not going to give us the trend in data. Is that what you're saying?
Yes, ma'am.
Okay, so you don't have discrete data here. It is the values are actually continuous. So you can see from the first month of 2014 to the 7th month of 2014, it is slowly increasing and reaching a point. So you have a continuous data here. Continuously you are collecting data, but you are specifically marking it as, till this month. So you are having some intervals where you are noticing the data. Monthly data you are noticing, but otherwise the data is collected continuously. Every day the data is collected. So every day the point in the orange line tells you how many visitors per day. In the blue line tells you what is the temperature in that day. So nonlinear regression can be used to fit the temperature data as well as the number of visitors data. But can you also tell me whether linear regression will make sense, any sense here? If you just look at monthly data, not daily data, will it make sense to have linear regression? If you just look at monthly data, in January it is the lowest. In July it is the highest. January lowest and July highest. Every year that's how so if you just take the July data every year, so from 2014 onwards till 2021 or 20, right? July only 20, till 20 only we have gone through July. So for 6 years, just look at the July number of visitors. They are of similar range. And it is the highest was in 2015. After that 2016 it is almost close. And in 2017 also you can expect the same. There could be a slightly higher or slightly lower only, but otherwise they are all in similar range, right? So we can consider to be the peak season visitors per year. So this year, what was the peak season number of visitors? Next year, what will be the peak season number of visitors? Can we answer from this data? You know the trend for 14, 15 and 16. So can you answer in 17 what will be the data? July 17 to 2017, how many visitors will come? Can we answer that question from this given data?
Yes, ma'am.
Yes, that is possible. So then at that point, if you consider only those points, then linear regression is definitely relevant. Am I right?
Yes, ma'am.
Yeah. So you have discrete values. discrete, not this continuous values, because continuous values will show you local ups and downs. But for discrete values, linear regression will definitely be very much suitable. And I mean, in that context, at least you can consider linear regression. But for continuous data, you may have to go for nonlinear regression models. So the wholesale price index, let us say how it is increasing. This is a nonlinear f of x. So 1960 to 1990, they've given some kind of data, yearly data they've given. So if you look at high level data, what is the trend in the high level data? If you go for very local changes, everyday change you want to capture, everyday trend you want to know, linear regression will not be sufficient. If you want to go for an overall picture, a higher level picture where across the yearly ones, so then this trend would be similar. So where the data is very similar, because you want to reduce, you want to put it in a straight line, which means the data should be increasing in a steady rate or decreasing in a steady rate. It cannot increase this year at a rate and decrease. The difference, the rate difference has to be really very close to the regression line. Only then that kind of data will be suitable for us. Local differences, if you want to find out, then linear regression is not definitely a good. So if you look at this graph that you see here, the orange second one, where you have up and down and up and down. Can you tell me of any signal which you have seen something like this? What type of data have you seen similar to this? What is given here is first differences. This kind of data, ECG signals are something like this. Correct?
Yes, ma'am.
Yeah, so ECG signals will be something like this. Any other example you can think of? Quickly, the changes are happening. Locally, there are
Stock
changes.
prices.
Stock prices. Yes, very good.
EEG signals.
EEG signals also look like this. The brain signals, they also look like this. Yes.
Microphone
Right.
sound. ma'am.
Sound, microphone sound. Yes, audio signals also look like this. These for these signals, the local changes are very important. You cannot capture the global change as well as the local trend. Global trend as well as the local trend you cannot capture at a time in any model. So which type of model? Regression type of model is more of a global trend model. It is more suitable for a global trend model, not for a local trend, unless specifically the local trends are also very similar. Most of the time it is not the case. The local trends are, really fluctuating, really changing. So for such things, regression model will be definitely not be able to capture all the changes in the trend. So this is about time series data. Now, if you look at this time series data, this particular case, the price of a particular item, you can even call it as a stock price. There is a global trend here as well as a local trend. Both things you can see here. If you simply summarize, you take an average for a given year. And if you look at the average, how it is changing every year from 1960 to 2010, actually it is steadily increasing. So do you understand what I mean by the global trend? The average per year is steadily increasing. You look at this entire graph. If you use linear regression for this, even if you use linear regression, though it is not able to capture the local changes in data, local trends in data, it definitely tells you what is the global change, the summarized. So a higher level trend you will be able to capture using a regression line in this particular data. So here you draw a straight line, it will go through the middle of this curve, and then it definitely tells you the orientation. and the average data. What is the orientation of the average data? That you will get if you fit a regression line in this particular data set, data points. So likewise, you can, depending on the data and the existing trend in the data, you can use a regression model. Now look at this data, retail sales from, basically 5 years. So 1991 to 2016. This is your regional sales, retail sales. Can regression fit into this line? Can you capture the global trend using a regression line?
Yes, ma'am, it's possible, ma'am.
If you put a regression line from 1991 till 2010 maybe, or 2009, that's more, it's almost 2009. At 2009, the global trend has suddenly changed. And then you have a new trend, new average from 2009 to 2016. So here you cannot have a single regression line that will go through the entire range from 1991 to 2016. So you cannot use a common regression for from 91 to 2016, you cannot have a single line. That's, a lot of error is going to be there. It's not like the previous curve where we had one line will be sufficient to show the increase in the average. Here the average increase itself is different. Better example is this one. You can have a regression line here at the bottom, and again after 1980 you have a totally different range. You can use a regression line here and then here. So when you have two different regression lines, then it is more of a classification problem. You have two different categories. Within each category, you can use a regression line for capturing the trend within that category. So you have two different groups. Whenever you have multiple groups, you have to first do the classification, then do a regression for each class. That is possible. Understood? So modeling time series data depends on what is the data, what is the trend in that data. By looking at these two data, this is one example, this is one example, this is one example. This one regression line is sufficient. This one, it has got two different categories. It's more clear here. Totally two different categories of data points are available. So depending on, by looking at this data points, you can actually decide what type of regression model, or whether we should use a single regression model or multiple regression models. First to do a classification and then do a regression model. Those kind of things you can decide by looking at the data. Is that fine? So we will move on to the other models from the next class onwards. Thank you guys. Thank you for today. Any questions? Any questions?
No, ma'am.
Okay. Thank you. Thank you guys.